Thanks for joining us for today's DFE webinar. My name is Jim Harlan, and I will be the moderator. Presenting is Aaron Hoig, Hypro Filtration's Operations Manager. If you have any questions for Aaron throughout the presentation, please enter them in the questions box on the right-hand side of your screen, and we'll get them answered at the end. With that, I'll turn it over to Aaron.
Okay, thanks, and thanks to everyone for participating in this webinar. We're going to be talking about DFE, which stands for Dynamic Filtration Efficiency. It's a new way of testing filter elements used in hydraulic and lube systems, and a new way of developing medias that are more stable and that better retain the contaminant that they've previously captured. This test method was pioneered by Hypro in the early to mid-90s, and we've continued to build on it and continue expanding the testing capabilities. So we start with a discussion on multi-pass filter testing, which the current ISO standard that manufacturers use to validate and develop their filter elements is called ISO 16889 multi-pass test. So we have a closed loop hydraulic system into which we add a known quantity and size distribution of contamination. The contaminant circulates through the system and through a test filter where we monitor particle count upstream and downstream from the filter element. So from this we get a removal efficiency, how efficiently the filter removes particles of different sizes, and we also get an idea of the dirt holding capacity of the filter element because we monitor how much contaminant is injected until the filter reaches its terminal pressure drop. So basic view of multi-pass filter testing. So a quick comparison of the two methods. ISO 16889, again, that's our industry standard. The biggest difference between the two methods, the ISO 16889 test uses one flow rate throughout the test. So the flow rate does not change, meaning the challenge through the filter does not change rapidly, and it doesn't really simulate what goes on in an active hydraulic system. This test more realistically simulates what would happen if a filter cart were connected to a system or some type of offline kidney loop conditioning skid were connected to a hydraulic or lube system. In contrast, the DFE test is an enhanced version of the industry standard where we can vary pump flow rate even to a ratio of 4:1. So if we're running at a maximum flow rate of 100 gallons per minute, we can drop that flow rapidly down to 25 GPM and then back up to 100 GPM, where we can more realistically simulate what happens in a hydraulic system. So the duty cycle looks something like this. If we were at low flow, we'd be at 25% of max rate of flow. We would increase the flow to 100% of the flow rapidly, monitor removal efficiency, stabilize at 100% of max rate of flow for 2 to 3 particle counts, and then change the flow rate again, back down to the low flow rating. And we do this continuously throughout the test. We may have 50 to 100 cycles depending on the interval and how large the element is. The other nice thing about DFE is we're sampling in a real-time, continuous manner throughout the test. So we have a really good profile of all particle counts all the time. So we can find any anomalies, any changes in efficiency, any unloading, or media breakdown. So this really gives us all the vital signs of the filter element throughout the stressful hydraulic system test. So this first graph gives us an idea of how an element that's validated to ISO 16889 actually performs in ISO 16889. So we're looking at a beta 5 sub C of greater than or equal to 1,000. So the red line is beta 5 sub C, and we see that throughout the test the efficiency is pretty steady even as the differential pressure starts to increase, which that's what the green line is representing. So on the next graph, we will show the same element that's validated to ISO 16889, but we tested in a DFE environment to see what happens to the same element if it are tested under more stress and realistic conditions. And when we do this test on this specific competitor element that was validated to ISO 16889, we see what we call media unloading. So the real emphasis of the industry standard test is to look at what's the removal efficiency. How efficiently does that filter element remove contaminant in a steady state environment? And what we're after with DFE is to quantify not only how well does that filter element remove the contaminant, but also how well does it retain the contaminant that is previously captured. This is critical, especially in filter elements that are protecting sensitive servo valves or other sensitive hydraulic components or bearings, where if an element becomes heavily loaded with dirt and it's not able to retain the dirt that it's previously captured when there's a change in flow, change in differential pressure, it can actually become a pretty dangerous source of contamination, releasing clouds of contaminant in a high ISO code that can cause damage to sensitive components or bearings. So what we see as the graph develops is when we go from a change of low flow to high flow, that's when we see the most dramatic unloading or drop in efficiency. So this filter element previously tested under the ISO 16889 method had an efficiency roughly of 99.8, 99.5% efficiency. But what we see when we test that same element under DFE is that the efficiency during transient flow changes even drops well below 90%. So not the filter that we really thought that it was when we test it in a way that it's really used. Here's a quick table comparison. So 16889, over the life of that filter element, it averaged 99.21% efficiency at 5 micron subsea and higher. The same filter element, time-weighted average, 96.82%. So that's a big drop in efficiency. And it leads to an increase in ISO codes. Also concerning is when we just isolate the flow change sequences where we go from low to high flow, we see that that set of average data points has an efficiency of only 91.5%. So even less efficient element. We also see this commonly in elements not designed and validated for DFE, that the dirt capacity is actually lower when you go to the DFE environment versus the ISO 16889. This next graph shows something that's more concerning than media unloading. So again, this is an element that was designed to ISO 16889 standards. And this filter element has a rating of beta 10 sub C greater than or equal to 1,000. And what we see early on in the life of this element is it does a pretty good job with stability, maintaining its efficiency. As the differential pressure increases and we have changes in flow, what we can start to see is actually a breakdown in the media, where the filter media may become fatigued, if it's brittle, if it's been damaged in the pleating process, or if it's just not properly supported for a stressful hydraulic system, we can see a breakdown in the efficiency at the rated size. The problem is you start to get particles that are much larger passing through the filter than what you would have if you were testing it to ISO 16889. So we see this breakdown in media efficiency. And you get a pretty dangerous filter that's unloading a high amount of dirt that it had previously captured. And it may not even reach terminal pressure drop if damaged badly enough, meaning it won't be changed, but will continue to bypass contaminant through the spots that are damaged. Also, when we conduct a DFE test, at the end of the test, we stop the flow rate, we take it down to 0, and then we turn off our injection, and then we wait for 30 seconds or we wait until we achieve a cooler temperature. And then we do what we call the Dfe Restart Test, which is we go from 0 to 100% of rated flow rapidly, and then we count particles downstream of the filter element. So in this case, we're not injecting any more dirt. We're only counting particles that came out of the filter element when we went from 0 to 100% of max rated flow. And if you weren't testing for something like this, you may not even know that it happens, and you certainly wouldn't know what to do about it. So in this case, just looking at the 4 micron sub-C channel, the blue line, this element that were previously validated to ISO 16889 releases almost 2,500 particles per milliliter downstream of the filter. So during this test, that same filter element would only release 26 particles per milliliter. Yet when we shut the system down and do the restart test, we see a huge increase, 2,398 milligrams per milliliter. Translate that to ISO codes. Before the restart test, there was an ISO code of 12.10.7. During the restart test, 18.17.13. So a huge increase in the ISO code, which leads to damage, abrasive wear, and sensitive components. The high-pro filter element rated for DFE, although we did not completely eliminate the unloading, the amount of unloading was greatly reduced. The ISO 16889 validated element had almost a 10 times the amount of contaminant released from it during the restart test. And this is a goal for high-pro. We want to be providing servo cleanliness fluid, ISO fluid cleanliness codes at all times, even during restart, even during dynamic stress points over the life of the filter, which we're achieving here of 15.9, less than 1, even after the filter is fully loaded and we hit it with a restart test, which that's the worst condition. So in summary, high-pro, we're not just concerned about capture efficiency or removal efficiency. We're also concerned with retention. So keeping those particles inside the filter element after they've been captured. It's dangerous to assume that every filter is like a black hole where whatever goes in never comes out. We know in dynamic hydraulic systems that that's not the case. Also, we use the DFE test to optimize our medias to achieve the lowest ISO code possible with not as much focus on a beta ratio. What matters most to customers is how clean is my oil and how long will my filters last. So that's our goal, is to achieve the best ISO code while balancing long filter element life and high efficiency. So some lab comparison testing. So the first set of bars that we show are results from the ISO 16889 test. And they show that both elements are true to their rating, beta 12 greater than equal, beta 12 sub C greater than 1,000. When we test the DFE environment time weighted average, we see that the competitor element comes in lower than the beta 1000, high-pro still maintaining its true rating. And then when we isolate just those sequences where the flow rate is going from high to low or from low to high, which is the most strenuous environment, we see that a high-pro still maintains true to its rating, and in this case, this competitor did not. It doesn't mean they're violating an ISO standard. They're true to the ISO standard. But again, the idea of DFE is we're making a filter element that's used in a stressful environment, and we want to test it in that same environment so that we can predict the performance in the field. It's a lot like buying an off-road vehicle and you only tested it on the highway when you use the antiquated ISO 16889 standard. So we want to test these filters in the way they're really used so we know what kind of cleanliness we will be delivering under any circumstances. Again, we see the percentage comparison at 4 micron sub C, 86.26 versus the Hypro 91.16. And as we see here in the dirt holding capacity, the Hypro also held about 5 more grams of dirt. Here's another competitive comparison. In this test, the competitor element actually has a higher beta ratio for removal than the Hypro element does. But once we get into the DFE test, then we see a drop in efficiency, consistent with unloading or media breakdown. And then when we isolate the worst conditions, which are the changes from low flow to high flow or high flow to low flow, we see an even bigger drop in efficiency on the competitor element. And the Hypro is able to stay true to its rating above a beta 7 sub C of 1,000. That's our goal. Again, these numbers are looking consistent with what we've seen before, 93.43% versus 99.17%. So the Hypro has a higher efficiency, also delivers lower ISO codes, 1391 versus 1612.1, and then greater dirt capacity, 38.45 versus 33.31. So a quick discussion on ISO codes will take us into some comparison field tests, and then a discussion on setting target ISO codes. And this is really what matters most to the plant. How clean is my fluid, using ISO codes as the unit of measure to quantify cleanliness or dirtiness, and then how long will my filters last? We don't want to be changing filters every other day or even every week. That's too frequently. So this is the ISO 4406 chart, and it shows ISO codes, and each code represents a range of particles. So in the first size that we look at is the 4 micron channel, and in this sample, the number of particles per milliliter were 151,773, which puts that count in the range of a 24 code, between 80,000, more than 80,000 up to and including 160,000. So then we would give that a code of 24. Then we look at the 6 micron sub C channel, and we see it's in the 22 code, so between 20,000 and 40,000. And then when we look at the 14 micron channel, we see that we're between 2,500 and 5,000 particles per milliliter. 33, 39, that's where we are, so that gives us an ISO code of 19. Now it's important to remember, as we drop an ISO code, we're actually reducing the amount of contaminant, we're actually cutting it in half. Or depending on where we are in the range, we could be dropping the amount of contamination even up to a factor of 4. This gives an idea of a micro patch with 100 times magnification. That's what 24, 22, 19 looks like. So 25 milliliters of fluid are pulled through a 1.2 micron patch, and then we look at it under 100 times magnification. Below that, we see a much cleaner patch that's at a 16, 14, 11. And on the ISO codes section of an oil analysis report, this is what we're looking at. We're looking at 4 micron, 6 micron, and 14. Those represent our codes, 4, 6, 14. So 16, 14, 10. Is that good or bad? It depends. Most often it depends. If it's for a filter that's in front of a servo valve, and that's how clean the oil is going into the servo valve, many times that's acceptable, but that's about as dirty as it can be. Many servo valves say oil must be kept at a 16, 14, 11 at all times. There are some servo valves, though, that are very expensive that we see on plastic injection molding machines now, and they're requiring a 14, 12, 9. which we can get to, but that's reducing the contaminant by a factor of 3, maybe even 4. So to do that, you need a plan. It's important to remember that ISO code values are ranges. So if you drop it one code, that means most likely you've cut the amount of contaminant at least in half. So if you go from a 16 to a 15, you may have cut it in half or even bigger, even almost by a factor of 3 or 4. And it's important to look at the details, the actual ISO code particle count values instead of just the codes. Or what most people tend to do is they just look at what it says on top of the oil analysis report. They get a status. Is it normal? Is it a monitor? Or is there danger? Or is it a critical? And we have to remember that labs have different criteria for their ratings. What may be critical for one lab may be normal for another. So it's important to understand what your target ISO code should be and then how to monitor them and how to interpret them. So this next slide shows a field test from a steel mill hydraulic system. In this case, there were 4 different filters that were upgraded to the Hypro 3 micron, which is the 5 micron sub-C greater than 1,000 rated DFE filter element. So we put those filters on pump discharge, servo, recirc filter locations. And then on the return line, we used a 25 micron just so we wouldn't be restricting cylinder unloading on the way back to the reservoir. And what we found, just by upgrading the filter elements and adding some breathers, was that we went from an ISO code of 17, 15, 12 down to a 12, 8, less than 1. Dropping the 4 micron particles per milliliter from a number of 970 down to 27. So a huge reduction in particles in the oil. Another successful application is on a paper machine main bearing lube, where just by upgrading to like-rated filters that are DFE rated from a beta 7 greater than 1,000 to a beta 7 greater than 1,000 Hypro DFE rated element, ISO codes dropped from a 2017-16 down to a 16-12-9. And on the 6 micron and larger channel, we actually had a 98% reduction in dirt in the system. Now we know that at least 75% of all hydraulic and bearing failures can be traced back to surface degradation from some form of contaminant. So if we can reduce particulate contamination by 98% just by upgrading the filter elements and doing nothing else, that's a huge amount of contaminant that we've reduced, and it's logical to think that we're going to reduce wear and we're going to reduce surface degradation, therefore extending the life of our hydraulic components and bearings. That's a big drop. This is the Hypro Dirt Calculator app for iPhone and Droid. And what we're able to do here is plug in a few parameters. So we plug in our system flow rate, 25 gallons per minute, hours of operation per day, 18, current ISO code, 2017-16, target ISO code, 16-12-9. And then we hit calculate and we plug results. So what we find is currently each year with a 2017-16, 371 pounds of dirt pass through that hydraulic component, pump, or bearing. If we achieve our target of a 16-12-9, there'll only be 23 grams or 23 pounds of dirt passing through that component or bearing each year. It's a reduction of 348 pounds of contaminant, or 93.6%. And we've reduced the contaminant load by a factor of 15. So that answers the question of how clean is my fluid? When you use a DFE rated filter, it's very clean. The next question is, how long will my filters last? So it's logical to think that if we remove the majority of the dirt or reduce the amount of contaminant in the system by 93%, once we collect all that dirt, our element life should be very high, because we know that when there's more dirt in the system, we tend to generate more dirt from the dirt that already exists. That's called the chain reaction of wear. So by cleaning up the system and getting to a new cleanliness equilibrium, then we'll have less contaminant being generated within the system, and we'll have longer filter element life. And that's what we saw here. Here is the original OEM filter that was being used, and then once we converted to Hypro, we began to drop the ISO code and some reduced filter element life here on the Hypro, but then again, long element life. And we even stuck a competitive element back in there just to make sure nothing had changed. So here's another paper machine lube oil application where, again, just by upgrading to a Hypro DFE rated filter element, we're able to drop the particle 6 micron and larger from 240 per milliliter down to 15 per milliliter. Another 93% reduction in contaminant, which we know will make our bearings and hydraulic components last much longer. So we have a little bit of discussion on target ISO code. How clean should my oil be? Different ways to look at that. You can identify the most sensitive component on the system, let's say a servo valve, and set your target fluid cleanliness accordingly to that. Another method for setting a target is to use a 7 to 8 step scoring process of how critical is this application. Is it a safety issue? Is there high pressure involved? Is it critical to my operation? And a few other key characteristics that we want to know about. And then by using that scoring method, then we will arrive at a recommended ISO code. We can also use bearing and component life extension tables where we can track, let's say we drop the ISO code from a 2017-16 down to a 14-12-9. That would have a profound effect on bearing or component life. Could be 3 to 4 times. The other approach is get it as clean as possible, and I say there within reason. You don't want to be changing filters every 2 hours and get that fluid so super clean, but you're consuming elements at a high rate and you're way below what your target would be. Get as clean as possible within reason and make it cost effective. This is a bearing life extension table, so we see if we're to go even from a 21-19-16 down to a 15-13-10, which is very clean for a bearing, but we extend the life of that bearing by 3 times. So a turbine bearing or paper machine bearing, steel mill roller bearings, just by taking the ISO codes down 3 to 4 codes can have huge effect on the life of that component or bearing. Cleanliness saves money. Once we achieve our target ISO code, there's less dirt in the system to generate more dirt, and our filter element life will grow substantially. If we're able to keep the fluids cleaner, we have fewer breaks, repairs on servo valves, pumps, cylinders that fail due to contamination-related issue. So we're actually able to lower our maintenance and labor costs if we use the high-efficiency DFE rated filter element. Also, if we can make the filters last longer, we minimize exposure to outside ingression. So we know anytime you open a hydraulic or lube system, dirt gets in, moisture gets in. It's even possible for air to become emulsified or entrained into the oils. So minimizing system exposure to the outside ingression is important. We want longer element life. Also, if we take care of these fluids like the lifeblood that they are for our hydraulic and lube systems, they're going to last a longer time. Again, that saves money. Also, when we improve cleanliness, we have better, more precise control and operation of automated type equipment. And if we can reduce ISO codes, we can also reduce unplanned downtime due to contamination-related failures. So we're pumping 320 pounds of dirt per year through a bearing. That's a lot. And then if we reduce that down to, say, 20 pounds per year, we want it even less than that. But that's a huge improvement, and we should see exponential increase in our bearing life. There's the bullet. Proper care of fluids from arrival to disposal is critical. People buy expensive equipment that's hydraulically driven. Shouldn't be using inferior filter elements. Using a DFE rated filter element will extend the life of the fluids and the life of the equipment and ensure a more reliable operation. And that's our last slide.
Great, thanks, Aaron. We did have a few questions asked during the presentation. Larry would like to know, why hasn't DFE replaced the old ISO standard?
Okay, yeah, that's a good question. To make a test stand that can handle changes in flow through the particle counters and rapidly change system flow at a 4-to-1 ratio, it's a big investment. And most of the test stands around the world are built around the ISO 16889 standard. Also, the technical committees are typically made up of filter manufacturers and large users. So it's difficult to get consensus on a new standard that would basically require everyone to buy a new test stand. So that's why we stopped trying to push it to be an ISO standard, and we just let it be our competitive advantage.
Great, thanks. In addition to that, Ron wants to know, what's the biggest difference you see with DFE rated filters versus those that aren't?
Well, that goes back to the point of, if you don't know there's a problem, you really can't fix it. So when we test filters under DFE, if we test a competitor element that we know isn't validated to DFE, we don't really know what's going to happen. We may see huge amounts of unloading. We may see filter media breakdown. It just depends how well the medias are supported and whether they've been damaged in the manufacturing process or if something else has happened. But the biggest difference we find is a filter element rated for DFE does not unload nearly as much contaminant as one that isn't, especially on the restart test. It can be a factor of 10, even up to as high as a factor of 20, where ISO standard validated filter elements unload a lot more contaminant than those rated to DFE. And also, we see bigger particles getting through. So the efficiency drops on the smaller sizes, and we also see larger particles that wouldn't normally get through on the ISO 16889 test actually passing through the filter. That's the biggest difference.
Okay, thanks. Just one more question, then we'll wrap it up. Dave wants to know, what's the biggest difference between DFE and the standard ISO testing?
Well, the difference is the flow rate change. So as we perform a DFE test, we are rapidly changing flow. We can do it as quickly as 0.1 seconds, going from a flow rate of 25% of max flow to max flow. So it's very fast. So the shock and challenge to the filter element is very dramatic. It can be, depending on how we set the test up. But again, it's just a more real-world way of testing these filter elements in a way that they're really used on a hydraulic system.
Understood. All right, thanks, Aaron. We're going to go ahead and wrap things up. Thank you to everybody that attended today. We really appreciate your time. Thanks, and have a great afternoon.